Good morning, everyone. Thank you for joining us today. We're about to dive deep into the very soul of our digital world, the operating system. It's this invisible yet absolutely essential layer of software that's running everything from the phone in your pocket to the massive supercomputers that are modeling our climate. It's really the foundation, the complex, elegant, and powerful foundation that our entire software-defined world is built on. And, understanding it is really the key to understanding modern tech.
This quote it absolutely nails the concept, doesn't it? I mean, you can have the most powerful CPU, the fastest memory, terabytes and terabytes of storage. You can have this whole orchestra of incredible cutting-edge hardware. But without the OS, it's just a pile of very expensive silicon. It can't do anything useful. The operating system, well, that's our digital conductor. It's what organizes all of that raw potential, directs every single component, and turns what would just be noise into a powerful symphony of computation. We're going to keep this metaphor in our minds as we go through this.
All right, so here's our game plan. First, we'll define the OS's role, really digging into our conductor metaphor. Then, we're going inside the machine. This is the fun part. We'll look at the core mechanics, the really clever computer science that makes it all tick. After that, we'll take a look at the modern OS landscape, checking out the major players and their very different philosophies. And finally, we'll tie it all together and see why this conductor is so incredibly important.
Okay, let's kick things off with that big picture view. At its most basic level, what even is an operating system, and what's its real job in the grand scheme of things?
So, what is the best way to wrap our heads around this? How do we take this incredibly complex piece of software and frame it in a way that just clicks?
Now, the technical definition here calls it a master intermediary, and that's totally accurate. But I think an even better metaphor is to think of the OS as the government of your computer. All your applications, your web browser, your video games, your spreadsheets, they're the citizens. See, the OS itself doesn't really do a single task you can see. Instead, it provides all the crucial infrastructure, kind of like the roads, the power grid, the legal system, that allows all those citizen applications to function, to coexist, and hopefully to thrive. It sets the laws, it manages shared resources so they don't fight, and it provides these essential services that keep everything running smoothly and securely. It really is the foundation that makes a whole society of applications possible.
So if we stick with this government metaphor, what are its main responsibilities? What are the absolute non-negotiable pillars of its job description?
Well, it really boils down to these three core jobs. First up, it's a resource arbiter. This is critical. It has to manage all the physical hardware, the CPU, the RAM, the storage drives, you name it, and decide who gets to use what and when. It ensures that apps can share these limited resources fairly without stepping on each other's toes. Second, it's a platform provider. It gives applications a stable and consistent environment to run in, plus a whole menu of services they can use. And third, it provides the user interface. The public face that lets us humans actually tell the machine what we want it to do. We're about to get into the nuts and bolts of each of these.
All right, now we get to go under the hood. From a computer science perspective, this is where it gets really, really cool. How on earth does the OS actually juggle all these complex, simultaneous tasks without the whole system just grinding to a halt?
Right. We all take this completely for granted. You've probably got dozens of browser tabs open, maybe some music playing, a file downloading in the background, and it all seems to be happening at the exact same time. But here's the thing. A standard CPU core is a sequential machine. It can only do one thing, one instruction, from one program at any given microsecond. So how does the OS pull off this incredible magic trick?
The magic here has a name: preemptive multitasking. And the hero of this whole operation is the OS scheduler. You can think of the scheduler as an unbelievably fast traffic cop for the CPU. It gives one program, let's say your web browser, a tiny slice of CPU time. We're talking milliseconds here. Before that slice is even up, a hardware timer goes off, yanking control back to the OS. The scheduler then does what's called a context switch. It perfectly saves the exact state of the browser and then loads the state of the next program in line, maybe your music player. It gives that program its tiny moment in the sun, and then the cycle repeats thousands of times every single second. It happens so ridiculously fast that from our slow human point of view, it creates this perfect, seamless illusion that everything is running at once.
Okay, next up is arguably the single most important innovation for making our computers stable and secure: memory management. How does the OS stop one buggy application from accidentally writing all over the memory of another app, or even worse, scribbling over the OS kernel itself and causing a massive system crash?
The key is this truly brilliant mechanism called virtual memory.
Just like it shows here, the OS gives every single program its own private, isolated, virtual world of memory. It's like giving each app its own private island. From the app's point of view, it has this beautiful, clean stretch of memory all to itself. It has no idea that any other programs even exist. This sandboxing is really the bedrock of modern security. But it's all an illusion. In reality, the physical RAM in your computer is a chaotic mess of memory chunks from dozens of different programs. The magic happens in the translation. When an app tries to access an address in its virtual world, a piece of hardware in the CPU called the Memory Management Unit, or MMU, intercepts it. The MMU then looks at a map called a page table that the OS maintains. This map translates the app's fake, virtual address into a real physical address in the RAM chips. This all happens at hardware speed, for every single memory access. And it's this trick that gives the OS total control, ensuring stability for everyone.
Okay, so the OS is a master of managing the CPU and memory. But what about the wild world of all the other stuff plugged into our computers? How does it handle the thousands of different printers, webcams, keyboards, and graphics cards out there?
It does this through a crucial idea called hardware abstraction, and the things that make it possible are device drivers. This little flow here shows it perfectly. A driver is just a piece of software, usually written by the company that made the hardware, that acts as a translator. So when your word processor wants to print something, it just sends a simple generic print command to the OS. The OS itself has no idea how to talk to your specific printer. Instead, it just finds the right driver for your model and hands off the request. That driver's only job is to translate that generic command into the very specific proprietary language that your HP or Canon or Brother printer understands. This abstraction is the whole point. It separates the application from the hardware. It means software developers don't need to write code for 1,000 different printers, they just write code that talks to the OS. The drivers handle the rest. It's genius.
So we just saw how the OS creates this abstraction layer between software and hardware. Well, it does the exact same thing for software services using something called an Application Programming Interface, or API. You can think of APIs as the menu of services that the OS government offers to its application citizens. When an app wants to do something important, like save a file or open a network connection, it doesn't just go and mess with a hard drive directly. That would be total chaos. Instead, it makes a formal request to the OS. This request is called a system call, and these system calls are the functions that the OS makes available through its APIs, like the ones you see here. And this is exactly why software for a Mac doesn't just run on Windows. Applications are coded to speak the language of a specific OS's APIs. A program that knows how to use the Windows API to draw a window has no clue how to talk to the macOS API to do the same thing. This dependency on a specific set of APIs is what creates and defines a software ecosystem. All right, our last question in this section gets to that third core job of the OS, being the public face. So what are the two main ways we humans actually interact with these incredibly complex systems? On one side, you've got the original, the command line interface, or CLI. It's basically a text-based conversation with your computer. You type a command, hit enter, and it responds with text. Now, it might look a little old school, but for developers and system administrators, it is an unbelievably powerful, fast, and precise tool. Its real superpower is that you can write scripts to automate complex tasks, which is why it's still the undisputed king on servers and in development. Then on the other side, we have the graphical user interface, the GUI. This is what most of us use every day. It was famously pioneered at Xerox PARC and then brought to the masses by Apple and Microsoft. The GUI uses this visual metaphor of windows, icons, menus, and a pointer. It's intuitive, you drive it with a mouse, and it's what lowered the barrier to entry and made computers accessible to billions of people. Okay, now that we have a solid grip on the core mechanics, let's bring this all back to the real world. We're going to survey the major operating systems out there today, and what you're going to see is that each one represents a really distinct and fascinating philosophy about how a computer ought to work.
This table gives us a great roadmap for what's coming up. You can see the 4 major players, and each one is defined by a core philosophy that leads directly to its key strength. Windows bets the farm on maximum compatibility. Apple goes the other way with tight integration. Linux is all about freedom and open source control. And the new kid on the block, ChromeOS, has this radical vision of cloud-first simplicity. Let's dive into each one. So, we have to start with the big one, the OS that has really defined desktop computing for decades now. What is the fundamental idea that drives Windows?
This number right here, which represents the historical market share of Windows on the desktop, well, it tells you everything you need to know about their strategy. Microsoft's core philosophy was to build an OS for an open hardware world.
It would run on pretty much any PC-compatible machine from any company. That strategy led to total market dominance. And that dominance created this powerful self-feeding cycle. Developers make software for Windows because that's where all the users are, and users buy Windows PCs because that's where all the software is. The result is its single greatest strength, just an unmatched world of software and hardware compatibility. Now, the flip side of that openness and supporting decades of old hardware, it also makes Windows a massive target for malware, and it can lead to what people often call legacy bloat, which can sometimes impact performance.
Okay, now let's completely switch gears and look at the philosophical opposite of Windows. What is it that makes macOS so fundamentally different? The philosophy behind macOS is all about total end-to-end control. People often call it a walled garden. Apple makes the hardware, and Apple makes the operating system that runs on it, period. This vertical integration is their superpower. Because the OS only has to run on a very small, tightly controlled set of hardware, Apple can optimize everything to work together in perfect harmony. And that tight integration, built on a really solid and secure Unix foundation, is what leads to that famously polished, stable, and smooth user experience. The trade-off, of course, is the exact opposite of Windows. It's expensive, people call it the Apple tax, and you have basically zero choice in hardware. You're not buying a platform, you're buying a complete integrated product.
Now for our third player, which isn't really a single product from one company at all. It's this massive, global, collaborative project. And that brings up a really unique point about how it's structured that we need to understand.
So technically, Linux is just the kernel, the core part of the OS that talks to the hardware. A complete usable operating system is called a distribution, or a distro. A distro bundles that Linux kernel with all the other system tools and a desktop environment. You can see a few of the hundreds of popular distros right here, each one tailored for a different kind of user. The core philosophy behind all of them is freedom. It's free and open source software, which means anyone has the freedom to look at the code, change it, and share it. This radical transparency and the total control it provides has made it legendary for security and stability. And that is exactly why Linux completely dominates the world of servers, supercomputers, and the entire cloud infrastructure that runs the internet.
So, here's the big question. If Linux is so powerful, so secure, so stable, and free, why isn't it the #1 operating system on everybody's desk and laptop? And this right here is the gap that Linux has struggled to close in the consumer world. Look, the open source community has created incredible alternatives for most applications, things like LibreOffice or GIMP. But many professional and corporate worlds are just deeply built around specific commercial software. The fact that you can't get native versions of industry-standard tools like Adobe Creative Cloud or Microsoft Office is frankly a deal-breaker for a huge number of businesses, creators, and students. And that's really what's held it back from wider mainstream adoption on the desktop.
And finally, let's look at the newcomer, an OS that really throws out the rulebook of the other three. What is the big idea behind Google's ChromeOS?
ChromeOS is built on this radical cloud-native idea. If you've always got an internet connection, you can dramatically simplify the local OS. For all practical purposes, the operating system is the Chrome web browser. Your apps are web apps, and your data lives online in Google Drive. This makes the OS itself incredibly lightweight, super fast to boot, and very, very secure. Since everything is basically running inside the browser's sandbox, it's really hard for malware to do any damage. This lets it run great on very cheap hardware, which is why it's so huge in education. The obvious weakness, of course, is that it really depends on having an internet connection, and it just can't run the kind of powerful, professional desktop software you'd need for things like serious video editing or programming.
Okay, so we've defined the OS, we've peeked under the hood at its mechanics, and we've toured the philosophical landscape of the Big Four. Now let's bring it all home and talk about the key takeaways.
After all of that, from schedulers and memory management units all the way to different market strategies, what is the single most important idea that you should walk away with?
I think this is the ultimate takeaway. Choosing an operating system is not just a technical decision, it's a choice that reflects your values. This visual here really captures it. Each OS points in a different philosophical direction. Do you value the almost infinite compatibility and hardware choice that you get with Windows? Do you prioritize the polished simplicity and seamless integration of macOS? Do you believe in the absolute freedom and fine-grained control that Linux offers? Or is your main focus the rock-solid security and affordability of ChromeOS? The OS is that indispensable, unsung hero of computing, our digital conductor, and the one you choose really does determine the kind of technological symphony you're able to create.
And that's really the bottom line, isn't it? These incredibly complex systems, they aren't just tools. They are the foundational platforms that define our digital lives, our economies, how we interact with information every single day. Understanding how they work, their strengths, their trade-offs, that's not some niche technical skill anymore. It's a fundamental literacy for navigating the world we live in. We have covered a ton of ground today. We started with the OS as the digital conductor, we looked at the beautiful engineering behind multitasking and virtual memory, and then we walked through the very distinct philosophies of Windows, macOS, Linux, and ChromeOS. Each one offers a unique set of trade-offs that shapes not just how our computers work, but how we use them to work and create. Thank you for joining us for this deep dive. For more explainers on the technology that shapes our world, be sure to subscribe to our channel, Tech AI and Beyond.